So in electromagnetics, we are interested about physical phenomena which can be described as fields. And they are related to we are more interested about a variation in the time domain as well as in the spatial domain. Okay? So when a quantity, so field is a quantity that describe a specific physical phenomenon. For example, in this figure, you see the amount of rain accumulate in a specified time period, say from 0 to 15 o'clock. Okay, so you see that in different places of Taiwan, you may have some more rain in Kaohsiung and some less rain in Taipei. So in this field, we can tell that the fields can be divided into the so-called static field and time-varying field. So as the name suggests, a static field does not change as the time changes, as the time varies. A time-varying field can be different at a different time instant. So for one example, how about the Earth's magnetic field, 地磁场? Is that a static field or a time-varying field? Well, actually, this morning I saw a news, or not a news, so news says that in the past few hundred years, the magnetic North Pole has moved from the north of Sweden to be, now it's very close to the geometric North Pole of Earth, and is still moving. Now, in the past few decades, the magnetic North Pole has moved more than 100 kilometers, so it's still changing. Okay, and right now it's moving toward the Siberia region of Russia. So from a short period of time, the Earth's magnetic field is a static field. However, if your observation of time period is elongated, then the Earth's magnetic field can still be a time-varying field, all right? And as the study of geometry suggests that, in fact, the polarity of Earth's magnetic field may change every 100,000 years. 10万年啊，大概地球每10万年到20万年，那个地磁会反转一次啊。Okay, so it's not a surprise that we are seeing some changes in Earth's polarization, Earth's gravitational magnetic field. And actually, what happens if the North Pole of Earth do switch to south in terms of magnetic field? Well, that would be, well, it depends on the rate of change. It depends on the rate of change. It can be the end of the world, literally. Okay, so in some movies, it seems to me that about 20 years ago, there are a lot of Hollywood movies. They are interested in about the end of war scenarios. And one of the common end of war scenario is the change of the Earth's magnetic field. So what happens? What happens if the Earth's magnetic field changes suddenly from the north to the south? Well, thunders. A lot of thunders. So if you have done some bad things in your early early stage of your life, do hide in the house, okay? Because there will be a lot of thunders. Why? Because according to Ampere's law, time variant magnetic field will be equivalent to electrical current. So there will be a lot of thunders. Alright, the other things in this slide is the fields can be divided into the so-called scalar field and the vector field. 存量场还有向量场。OK， 刚刚讲的是固定场跟时变场，现在我们看到的是存量场跟向量场。So of course, as the name suggests, a vector field can be described is described in terms of vectors, while a scalar field use scatter to represent the field. So here's one example. In this example, we are observing the height. That is the elevation above the reference ground. So one example is equation 1.50. You have hxy. So to the left is the description of the function. H suggests this is the height. And in the parentheses is x and y, means height is a function of position. That is the x-axis and y-axis. And to the right is 6 minus 2 times square root of x to the square plus y to the square. That is the description of the height in this area. And it's actually a cone function. 角锥一个角锥的结构cone function. So as you can see, to the right you have a function, you have an equation involving description in x and y. Okay, and to the right are two figures. This is refers as the top view. You're looking from top. And how about this one? This one is referred to as the perspective view. 记起来吧，我们念麦嘛，对不对？给他们有一个英文嘛，OK。Perspective view 侧视的，侧边看过去的Perspective view, top view side view Just what it looks like if we do the side view. It's just a triangle and there are circles. So what those circles suggest? Those circles suggest the equal field line. And in this case, is equal altitude or equal height. So the circle in the middle is the, well actually the point is 6. This is the circle of height equals to 4. This is the circle of height equals to 2, and this one, the larger one, is 0. Okay? So you can use graphical muscle to illustrate the variation of the function in space. And in this equation, you don't have a description about t. So it means that this is a static field. And well, I think it doesn't hurt to describe to push a little bit further. In the study of electromagnetics, we will come up with some spatial operation, 空间的操作所以我要讲的空间操作指的是空间的微分 spatial derivative. So in chapter 2 and chapter 3, you will come up with this symbol very frequently. So, do you still remember the implication of this symbol? What does that suggest? Well, of course, in your first year, in the engineering calculus, you must have come up with these operators. So this is the so-called del operator, okay? And what is the implication? This is spatial derivative, 空间的微分，空间的微分，倒三角。However, here comes the more complicated part. Well, there are different kinds of spatial derivative. Say you have curl operation. You have divergence operation. You have gradient operator. So be careful about the difference. You see, the curl operation is a spatial derivative for a vector in the space. And the divergence operation is also a spatial derivative operation on vectors. And this one is referred to as gradient. OK， 好，中文给你啊，这叫梯度，这叫散度，有没有听过？好，太好了，感谢你的集齐哦 ，OK， 这个叫旋度吧，写错字了 ，OK， curl叫旋度了，OK。So actually, the curl operator, as you can see, it's in the form of cross product. Divergence operator is in the form of scalar product. So actually, this will result in another function, another vector. This one will give you a scalar because this is scalar product. 不要写错啊，写 V 好了啦。Okay. So how about this operator? As you can see, this is a spatial derivative on a scalar. It refers as gradient. So what is the result of this? Is that a scalar or a vector? It's a vector. Gradient ends up a vector. So what I mean to say is, if you perform gradient on H here, it will give you what? It will give you T度。That is the description about the slope on this cone. It not only give you about how large is the slope. 就是它倾斜的那个倾斜的程度，它告诉你倾斜的程度。It not only tells you how large is the slope, it also tells you the direction of the slope. So the result of a gradient operator will give you a vector. And in this case, the gradient of height will tells you the slope of the at a different position, and it will also tell you the direction of the slope. So in this case, so if you do the gradient operator at this place, what is the direction of this slope? 你觉得它的那个取梯度之后的方向会在哪里？你觉得是这样还是这样？找回定义啊！我们刚才讲说，这个东西是什么 ？OK。Well, the gradient, by definition, gradient shall pointing toward a direction of the physical quantity of larger value. So this, here is h equals to 6. Here is h equals to, say, 2, okay? h2 equals to 2. So the slope shall pointing toward a quantity of larger value. So actually the operator of the result of this of gradient operation of h should be this way. And this leads to a very important issue in electrical circuit, in the study of electrics. That is, about 200 years ago, when we write the textbook of electric circuit or electrical field, we do the definition incorrectly. That is the definition of voltage in electrical field. Well, actually, I bet you have seen that. What is the relationship between electrical field and voltage? Well, what is the relationship between electrical field and voltage? It's actually the gradient of voltage, the negative of the gradient of voltage. So if you have a capacitor connected to a battery, and here's the ground, so you have a larger potential here, smaller potential here. What is the electrical field? Well, this is the electrical field. However, because you have V and V equals to 0 here. But if you do the gradient of V, it's actually should pointing upward, not downward. So when we do the definition, it actually, we fumbled in this case. So it ends up that in the representation of Maxwell equation, there are a couple of negative signs. And all those negative signs are inherent with this mistake. 所以因为一些历史的原因所以我们在电磁学的那个 Maxwell equation 里头，其实有一些符号怪怪的不是很顺其实就是因为我们在定义电位的方向跟电场的方向跟电位的那个高低的时候弄错了OK， 所以好了没关系了，反正习惯就好了OK， 来。Alright, and here's another description. Okay, so here's another function. This function is actually what? The distance of your observation point from your observation point to the origin. So the function is relatively simple. R as a function of x, y, z is expressed as the square root of x to the square plus y to the square and plus z to the square. So as you can see here, again, this is the description of space. It's the description of the space. And it ends up with the distance from the origin. And to the right is a graphical representation of this equation. So what are the implications of these lines? Well, it actually shows the projection of equal distance sphere. Because as this equation suggests, you know that equal distance geometry shall be larger sphere and smaller sphere. And the projection of the spheres on the xy plane, yz plane, and xz plane, the three principal cut, shall give you circular lines like this. And this kind of suggests that the equal distance geometries are spheres, larger and smaller ones. And here is an example of time varying field. One example is temperature. And so for temperature, a general expression for temperature can be written as T, the capital T means the temperature, as a function of x, y, and z, which means temperature are a function of position. And the lowercase t means it's a function of time. It's a function of time. And the study of temperature, we may illustrate the temperature variation in terms of constant temperature geometries or the so-called isothermal surfaces. 英文时间到 ，iso 是什么意思 ？iso 这个字首是什么意思 ？the same the same 相同的所以 iso 所以you heard of the ISO 9000 series of ISO 14000 ISO 9001啊 ISO 9002嘛那个标准其实要是告诉你，就是说这是一个一致性的标准OK 所以 isothermal means the same temperature isotropic meaning the same in the space isotropic. So here's the example. Well, this is actually the topic of my doctorate dissertation. 所以有人问说，老师你博士论文做什么的？博士论文是挖地雷的。真的，你小看挖地雷这件事吗？世界上有几百万颗地雷啊，威胁着千万小朋友的安全啊啥的对不对这是很 serious matter OK Well, but in fact, in my case, I'm more interested about the so-called anti-vehicle landmine, not anti-personal landmine. Okay. And however, this is still an important issue. Of course, when it comes to the Ukraine war, actually the anti-vehicle mine is deployed widely, and they plays important role in this conflict. So, for a military operation, it's critical. Well, anti-personal mines, as we see from the Hollywood movies, they kind of hide and they are disguised so that you cannot easily identify the location of anti-personal mines. So it will explode or surprise you by explosion. But the anti-vehicle mine is kind of, they just lay on the ground. So if you move close enough, you can see those landmines. So the most important function is saying that, well, do not pursue further. Stop your tank, stop your vehicle. You shall not proceed. So for the United States Army or United States Force, they are more interested about to find the anti-vehicle mine in the early stage, so that they can plan how to pursue their enemy as their enemy retreat. So one approach is use airplanes to survey the area of interest. So to detect those anti-vehicle mines remotely, how can you do that? Well, you can use cameras. But unfortunately, those anti-vehicle mines are painted in green and brown, so that on the optical cameras, they looks very close to their neighborhood, like the grassland or dirt land or earth or sand. So it's probably not that easy to identify them from a distance on an aircraft. Okay, but Of course, if you have UAV, you may fly at a very low altitude, and it probably can give you a clear vision. So an alternative is to to survey the ground using infrared camera. And infrared camera do detect the difference in terms of temperature. Okay, so the temperature difference shall make more difference in terms of infrared. 有没有看过阿诺以前的那个片？叫什么？魔鬼战士吗？还是什么？反正就是那个外星人的那个，有没有 ？OK， 我小时候最喜欢看那个片了。OK 啊，里头那个外星人他们怎么样去感知那个世界的？就用红外光嘛，对不对？所以我们说啊，因为那个外星人的母星，他们那个太阳是比较红的，比较没有像我们的太阳温度那么高的。OK， Alright, so what I've done is use some numerical method to calculate the temperature variation on an anti-vehicle mine. So here you see an anti-vehicle landmine, okay? And because of the sunlight, as the sun rises, the solar irradiance on the landmine and on the ground surfaces will increase the temperature of the landmine and the grass as well. However, because the specific rate of absorption specific rate of absorption is different between homogeneous materials such as metal surfaces or plastic surface and the grass. So the temperature difference becomes more and more obvious as the time progresses. So as you can see here, during the noon, the temperature difference is more obvious between the landmine and the grass. However, at say early in the morning, say 9 o'clock, the difference is less obvious. So it tells you the result or the implication of this study tells you that if you want to detect landmine using infrared, you should go in the midnight or in the noon. Okay? So it's just an example of the temperature file. All right, so, okay, I should move a little bit faster. So in this page, we are talking about how to represent a vector field. A vector field has two quantities. One has two descriptions. One is the magnitude, the other is what? Direction. So a vector field is described in terms of its magnitude and direction. So how do we represent a vector, or how do we illustrate a vector? So here are some examples. First, we can decompose the vector on the three reference directions. So as we have seen already, so AR can be decomposed of its projection on the X direction, Y direction, and Z direction. So equation 1.52 is a general expression for a physical quantity of time and space using a more complete representation. So to the left is the scalar. As you can see, F is written in bold face, 粗体字嘛, And the parenthesis suggests it's a function of space and time. And it can be written as Fx, Fy, and Fz. So Fx, Fy, and Fz are its projection of F on X and Y and Z direction. They are also function of X, Y, Z, and T. So that's the reason why I say the math involved in electromagnetics is not difficult. It's just burdensome. 有点烦了OK， 你试着要写的有点又臭又长的OK。 difficult once you get used to it, right? So 1.50CA and 1.50CB are vector representation in cylindrical coordinate system and spherical coordinate systems. So be sure to replace XYZ as R phi Z and R theta phi in cylindrical and spherical coordinate system. So next thing is the flux line, the definition of flux line. So the vector, the direction, we know that a vector is more interested if it is not homogeneous in space. So if it changes its magnitude and direction as it moves along in the space, then the description of this vector can be more interesting. So suppose that we have a vector, physical quantity, move along on the red line. The tangential direction, 切分方向 is the line direction locally. You can think of the tangential direction is the direction in a local position. So at this point, the line pointing to upper right, while at this position, the line direction is pointing to the right, upper right and right. So they may change. And this tangential direction refers to equals to the so-called differential lines. Differential line, DL. Okay, as we already defined in previous lectures. So DL, differential length is in parallel with the tangential tangential lines is in parallel with the direction of the vector. And to claim that the differential line and the vector are in parallel. To claim that they are in parallel, they must change in proportion in all three directions. 所以想一下这件事情了所以假如你要宣称说一个物理量的方向跟它的那个线差分向量是平行的话，那就表示什么？表示物理量的变化跟线段的方向的变化，也就是线段在 XYZ 或者是任意的3个 reference direction 上面的变化量，那个变化线段的变化量跟物理量的变化量是等比例的 in proportion. So based on this argument, based on this result, we can write out equation 1.54. That is, if you describe the vector in the Cartesian coordinate system, the differential length in x, y, and z direction, that is dx, dy, dz, is proportional to the changes in f in x direction, y direction, and z direction. So you can, for a local position, for a local observation point, you can write down this equation, that is dx over fx equals to dy over fy and dz over fz. That should be true for the vector and for the vector. And equation 1.55 and 1.53 are the same thing in cylindrical and spherical coordinate system. And the thing that you need to be aware of is r over here, and r sine theta over here. Why? Why do we need this adjustment? Because in cylindrical and spherical coordinate system, phi phi are not lengths, they are only angles. So you need to specify the distance from of your observation point to the origin or your observation point to the z-axis so that you can have a differential length. Okay? So to be careful about this in cylindrical and spherical coordinate system. And in this slide is the indication of vector field. So which one do you prefer? Well, I'm more used. Well, I guess most of the people are more used to this kind of description. So you use arrowhead to specify the direction of the vector field, and you use the length of the arrowhead to specify the magnitude of the vector. However, there are some alternative expressions, such as this one. This one using the density to specify the magnitude of the field. And the arrowhead still pointing toward the direction of the vector field. So we may have some other different representation, but I guess the two are the most common ones, all right? And in this example, we will introduce another important idea, that is omega. Omega is the so-called angular velocity, 角速度, angular velocity. Well, we will come up to omega. It's not W, all right? Be careful about that. It's actually a Greek letter, omega. Not Roman letter W. It's omega. So omega, the angular velocity, is the velocity with respect to the axis of rotation. So it's a vector field. So let's see some definition about angular velocity. So one of the important equations about angular velocity is V equals to omega times R. V is the velocity, the actual velocity. It equals to R times omega. So imagine that you are a small ant on a rotating disk. Then, depending on your position with respect to the rotating axis, 根据你到旋转轴的那个距离，你的实际速度就会有所变化。即便在那个唱盘之上，你的 omega， 你的角速度都是一样的。但是因为你跟旋转轴的间距不同，那你的实际速度就会有所变化。So the velocity equals to the product of angular velocity and the distance to the rotating axis. So as you can imagine, or as you can see from this graphical representation, if you are closer to the rotating axis, the arrowhead is smaller, and if you are away from the rotating axis, the arrowhead is larger. And the arrowhead direction specify the direction of the vector field is that position, which is tangential to the circle. So as you can see here, it's still the same. So finally, let's have an example. It's an example of, this example shows you the idea of angular velocity. It also shows you the application of changes of coordinate system. So it's a kind of a practical problem for section 1.3. Okay, so here we have this equation. So what do we learn from this equation? We know V is a vector. The velocity is a vector. And this V is specified in which the coordinate system. It's specified in polar coordinate system. So it's written as R phi. And therefore, it's written as omega r a phi. So a phi shows you the direction of the velocity is in parallel to the phi direction. And the magnitude of velocity is the product of omega, the angular velocity, and the distance r. So as r increases, the velocity becomes larger. So you have a larger velocity on the outside, smaller velocity on the inside. And because this thing is written in the polar coordinate system, so the vector itself and the differential length can have this relationship. So dr, fr, not that for v, does it has any projection on the r direction? No. Oh, so the projection of VR always equal to 0, according to this equation. So this is the general expression for vector v in polar coordinate system. So as you can see here, it has no r component. It has only phi component. So dr over 0 equals to r d phi over omega r. So r is a constant, which means this end, 这只小蚂蚁, will always rotate it in the same circle of r. And in this slide, it demonstrates how to convert the description of the vector in the polar coordinate system into Cartesian coordinate system. So you can refer to the conversion matrix in section 1.3. That is, you find out the projection of WR in the x direction. So WR itself here you have V5 times AX dot AX. So you have you effectively find out its projection on the x-axis and the projection on the y-axis. So you end up with WR minus sine phi AX and cosine phi AY.这个我要注意一下哦，你可能自己要想一下，为什么会有那个负号在那边？为什么有那个负号在那边？假如说我们是这样转好了哈，所以 AX 是哪个方向？这个方向。这个方向是什么 ？A phi， 对不对？这个方向是什么 ？AY， 然后这个角度是 phi， 所以呢，这个角度是多少 phi？ 好，所以你看看 A phi 在 x 方向的 projection 是什么？等于这一段嘛，它的 projection 是这一段，对不对？这一段等于什么 ？sin phi。但是注意哦，这个箭头是往这边过去的，所以它其实是负的 sin phi， 哦，所以有没有负的 sin phi？ 然后 y 的 projection 呢，就比较简单了 cosine phi， 哦，所以自己要小心哦。为什么有那些负号在那边？它其实是跟那个参考向量的夹角还有它们的方向是有关的So be careful about the direction it shall matters in terms of negative sign or sign. Okay. So finally, you can use what? Or you can substitute r sin phi as y and r cosine phi as x. So you end up with this relationship. Okay. And using the general form of differential length in the Cartesian coordinate system, you end up with this relationship, and it's, as you can see, it's identical to a circle. Alright, so here's another summary. This slide is the summary of what we can do when perform the conversion of vector in different coordinate system. So this is an example for converting a vector in the cylindrical coordinate system or polar coordinate system into the rectangular coordinate system. So you are recommended to review these slides at home. All right, so that should conclude our